So you will need to get through with me for an hour and a half more, an additional hour and a half, I'm sorry. To impose on you this. I will substitute for Dirk Meissner, who suddenly is very busy. So we will follow the same routine. This is the continuation, science technology policy. Four good papers again. We think 15 to 20 minutes each, maximum 20 minutes with maybe 5 minutes for discussion. Okay? All right, so without further ado, I want to ask Vitaly Rudь here to start with the first paper, which is on knowledge production function. Vitaly.
Yeah. Thank you for the announcement. My name is Vitalий Rudь. I'm a senior researcher of the Laboratory of Economics of Innovation here in Higher School of Economics. What I'm going to present is a kind of an maybe somewhat more academic exercise as opposed to direct applied papers discussed in the end of the last session. It is an outcome of a special project which we are having for quite several years in our institute, in our laboratory, and this study is one of the contributions in the agenda of heterogeneity of innovation behavior, which is a kind of an umbrella topic for a lot of our studies, because we one of the key, let's say, passions that we have in our studies is to treat actors not as some unified and well, let's say homogeneous entities, but those who are diverse and understanding their specificities and diversities and understanding the consequences which it brings on one hand to theory and on the other hand on the policy making also. So I'm going to talk about and knowledge production functions. This report is based on a unique asset provided to me in a special regime within the ISSEC. It includes, it is a large database of Russian innovation survey and includes quite rich data. And this extensive data set allows us to model and to quantify the innovation in great detail. And that's what I am going to talk about. To start with the common approaches, which are kind of generally accepted as the most useful and impactful to address the innovation performance of the companies. Then I'll quickly describe the baseline model and the core observations which can be made, which are relevant for Russian specificity of innovation. And then I'll pass to this topic which is of extreme interest to me, the heterogeneity of innovation behavior. Well, I'll start with a, let's say, this is a kind of a general idea of innovation studies, and one first entry point here is that the story of innovation studies of last, let's say, 40 years is a story of endless growth of complexity. So starting from quite straightforward approaches like linear model, like heavily in R&D based understanding of innovation and economic growth, we come through a very complicated concepts like imitation-driven strategies, open innovation, and even less formal things which are now on top of the agenda, like user-driven innovation, public sector innovation, and others. All also the factors, the dimensions and the theories to explain this diversity grow in dimensions, in variables, and in and the demand on data and evidences sometimes is overwhelming. At the same time, the existing STI measurement framework is also developing very actively, and as soon as it is designed in a very sophisticated way, it provides facilities to account for all of these novel concepts with a more or less specificity. So the existing data sets on the innovation actually allow us to explore a lot of things. The key challenge here is that usually the studies follow one selected pathway, while the diversity and heterogeneity sometimes is left at a certain point. This is all what we are doing in our Laboratory of Economics of Innovation, bringing these dimensions together. This specific, if one would be to analyze the innovation and performance, first thing which comes to mind, and kind of a naive approach to correspond the innovation inputs in this or that way, like R&D expenditure on innovation, and the effects on firm performance. However, this approach is known to have certain issues because, I will not go through them in detail because you can easily find them in most of the relevant literature, but these issues impose certain challenges to econometric modeling. That's why, quite long ago, extremely brilliant scholars like Zwigory-Liches and Peix and others introduced a sophisticated multi-step approach in order to treat all these complications. And in its present form, it can be understood as a sequence of four more or less connected steps. One is to explore the factors that influence the propensity to innovation, that means factors that influence the decision to engage in innovation. The other one explores factors that increase the innovation expenditure, the amount of expenditure spent by the company. Then another thing is how the intensity, how the innovation expenditure, innovation input turns into innovation output. And the last step is to understand how the innovation output helps general economic performance, because this relationship is far from being straightforward. Usual econometric models vary depending on the quality of the data that is available. A common approach based on the CIS type studies, the International Innovation Service, is to use some cross-sectional adaptation of the model. The model is usually called Crepon-Duguet-Mairesse model, the CDM model, after the authors who published it in 1998. And this study implements this model for Russia. Several words about the data. So as I say, we are accessing in a special limited regime the data set of the Russian Innovation Survey, the official survey which is annual and mandatory and covers quite most of the medium and large companies in mining, in manufacturing, and in utilities. Here are some descriptives, some general ideas on the filtered data set. You can find the aggregates, the official aggregates, in the data books published by Rosstat and by Institute of Statistical Studies. here are the specific descriptives based on the data. So that means that annually there are like roughly 20,000 observations, but due to low innovation activity of Russian enterprises, that means like 1/10 of them only is the innovation subsample. But still it's quite a lot. For the conceptual model which was described the previous slides is specified according to the slide. So basically we model the propensity to innovate as a function of firm size, of competition, of certain availability of resources, of some proxies of human capital like share of university graduates. Then the intensity also is connected to the competition regime and the availability of the raised funds as contrary to the own funds invested by the company. Also the proxies for continuous engagement in R&D are presented and the cooperation strategy is controlled. The efficiency is mostly relates the innovation expenditure and in presence of the productivity, because one of the limitations of this process is that the more productive companies are reasonably expected to be better also in delivering innovation and vice versa. So that helps to refine the special technique of simultaneous equations help to refine this influence. Okay, the last equation finally introduces the most interesting coefficient, how the innovation sales are transformed in actual economic performance gain. At the first step, we estimate the baseline model. Here is a key structural coefficient for the equation of the propensity to innovation. This is how the company size influences the probability of engagement into the innovation activity. So this is the coefficient estimated in separated cross-section every year. For this visualization purpose, the confidence intervals are provided, and this illustration in fact shows high stability of the estimates of the for this particular equation. There are some specific observations like human capital is highly significant for engagement into innovation. Then access to extra resources as being a part of a business group or being a state-private enterprise influences the process of engagement into innovation positively. Ambition like addressing national and international market as opposed to local ones, and but unexpectedly the degree on reliance on international markets is not that important. Similar equation can the similar presentation is for the innovation intensity coefficient. It is a bit harder to interpret because the coefficient, this elasticity is negative. The elasticity of transformation of firm size into the innovation intensity is negative. That means that firm size grows faster than per employee investment in innovation. So in fact the investment of innovation is quite scarce, but there is an interesting illustration to the standard theories about the inverted U-shape relation between intensity of innovation and the competition. We can see this U shape. However, I should stress here that this is a proxy of market share, and let's say 85% of companies are far below this high point of this parabola. So for them, the size and the market share have only positive effect, and for the huge ones, for the monopolists, indeed there is a negative relation between market power and innovation intensity. Then, speaking about the efficiency of innovation, first we can see that it is a bit less robust over years. It is not that straightforward to interpret the changes, the yearly changes of these coefficients, but still only a fraction of them is significant. And if you imagine this average level, you'll see that most of the coefficients do not get away from this confidence interval corridor and the significance corridor. So still, also this equation is very robust. There is a very high impact of general productivity, so basically good companies are also good in doing innovation. And the last, but one of the most intriguing equations is about understanding the actual impact of innovation to total sales. Let's say this is an elasticity. That means that this coefficient shows that if innovation sales are increased by 1%, that total sales are increased in something like 0.2%. It's also subject to influence on the human capital, the relevant markets, and there is an interesting effect that state companies are not good at benefiting from innovation. However, the foreign ones are the most getting the most of innovation introduced. So we saw quite robust estimates that are lasting over the years, but actually the challenge of heterogeneity is to go into the deeper specifics, and for this study the sectoral specifics is discussed. There are a lot of theories to discuss the origin of the sectoral specifics of innovation strategies, and the most important thing is that the existing measurement framework provides us means to measure, to control for it. How do the theorists deal with this heterogeneity? There are several approaches. There are, let's say, a row of approaches. A usual way to deal with it is to employ some kind of taxonomy. There are different principles to base the taxonomies. As we are limited in time, I will skip the most, let's say, famous things. But we can fix that. We can do it using the case-based studies of sectoral practices. We can use some one-dimensional classification as the famous high-tech, low-tech classification when we focus only on the R&D intensity. We can exploit some multi-dimensional but still aggregate variables and produce some more interesting or more rich classifications. Or we can go to the firm level and derive the classification using the clustering exercises and finding the and meeting the sectors that share the same distribution of different types of innovation companies. And all this portfolio is quite rich, but what is proposed here is another approach. Basically, what we are developing in this paper is to cluster the industries or classify the heterogeneity of industries according to the statistical significance of the differences in the production function. So basically, we want to join in the same taxonomies, in the same classes of the industries for which the knowledge production function is not significant, is the same basically. So this is still under constant improvement. This is a preliminary effects of the sectoral fixed effects of the of different industries. And one important implication here is that the four dimensions, that is propensity, intensity, efficiency, and impact, are not equally aligned. That means companies can be much more eager to engage into innovation and by the way, this corresponds to the classical high-tech, low-tech scale. But in terms of intensity of innovation, in terms of economic impact of innovation, sectors could be very diverse. And this encourages the further investigation. We have a preliminary results for the final clustering of the taxonomies based on these tests of significance of the differences between the production functions. And basically, here is the first attempt of this classification, and we can see that according to this principle, sectors are divided into this not that straightforward to interpret groups, like somehow mining and utilities and other, and food, and also petrochemistry is joined in one which is low in intensity and low in efficiency of innovation. As a contrary, there is quite a large group which is quite high in terms of intensity and impact and efficiency. Still, this is subject first to refinement of the methodology, because now it is a bit mechanical, but because it tests, okay, I don't go into this detail, but still this is a first promising result, because according to some logic, this taxonomy guarantees that the knowledge production function within these sectors is the same, basically. So this is the principle of classification. And and to add a couple of words, as soon as we are on the research policy section, science and innovation policy, there is a clear understanding that these enterprises possessing different knowledge production function will eventually have different reactions on the same policy instruments. So basically, and maybe also different types of enterprises could be could be addressed differently for different objectives. For example, if we are interested only in increasing the total expenditure of innovation, we could focus on those who are those industries which are good in this intensity equation. And on the contrary, if we are more interested in the long-term impact and returns, maybe these enterprises that are that already benefit more could be subject to some attention. So thank you.
Thank you, Vitaly. This is very rich type of research. Take me to the previous slide of this. Very rich, and to show you how where we are still. It's very interesting that in this category right here, it strikes me, you get some of these sectors that everybody, all developed countries and emerging economies keep looking at, but I see here lower efficiency. I see some interesting things, and this category includes pharmaceuticals, where there is a big problem. And it includes computers. So these are very interesting results. Questions? We have time for one or two questions on this research. Yes? Good.
Thank you very much. Very interesting study. I'm very interested in study modeling, but I know that in last years there is tendency of including some dynamic aspects in the innovative input and output equations that allow to reduce heterogeneity and to get more reliable results. As I see, you have quite large data. Do you have possibility to form panel structure and to analyze the model in dynamics and to get more reliable results?
Unfortunately, as soon as it is anonymized data and the access is restricted, there is no possibility to construct a panel. I only can do propensity score matching, but there are a lot of studies which say that it is not an appropriate way to construct this pseudo panel. So, I mean, we are in the kind of a balance between inefficiency caused by cross-section and inefficiency caused by this cross-section. But maybe I'll, well, I mean, it could be one field for experiment.
Okay, I don't see any other questions, so we should better move to the next. Paolo Zakkia, talking to us about cities.
Yes. Should I sit there? How
Yes, please.
Thank you, Vitaly.
This is the easiest.
So I will keep it short because I mean time is a huge issue here.
Yeah.
I am Paolo Zakkia. I come from Italy, and this is joint work with my co-authors Alexandr Stepanov and Helena Švajger at the European Bank for Reconstruction and Development. And this paper is about the long-run effects of the Soviet-era science cities on today's outcomes in the Russian economy, both at the municipal and the firm level. So again, like Vitaly's, this is also very much academic study in spirit. It has to do with a general search for the effects of place-based policies by the public policies by the government, especially those with the innovation dimension. But we feel that this paper has also some policy relevance for Russia. Like the usual story about Russia is that it needs to diversify its economy, its firms to become more innovative. We want to see whether specific kinds of policies may have a positive effect in this regard. So what do we do in this paper? As I said, we study the long-run effect of previous investment in R&D by the Soviet government, and we assess this effect both at the city and at the firm level. We feel this is the first paper that does so in a systematic and an econometrically rigorous way. And we also bring to the table a new data set that we have constructed. We've made a huge effort in this respect. I'm going to talk a little bit about this. What's our methodology? We have two separate analyses. One is municipal level and the other one is firm level. For municipal level, which admittedly is the one we have focused the most on because the original policy, the creation of Soviet science cities, was actually it has this unit of variation. It was something at the city level. So what we do, we try to compare cities where that became science cities to other places that they look exactly like them at the time of the enactment of the policy. So the idea is when the Soviet government decided to establish a science city in a certain location, we want to see how it compares in the long run in today's Russia with respect to other places that might have been as well selected for such a location. And we have a background story for this. As for the firm level analysis, it is more descriptive in nature, and we try to actually we have data. We have tried to do something in the spirit of the CDM model described by Vitaly. It doesn't work very well. I will talk a little bit more about that later. But here are our main results. Today's science cities still host a more educated population with respect to historically comparable localities. And nowadays they still provide more patents, they realize more patents, and they seem to be more economically developed than matched urban areas. However, they are not that much larger in terms of population, and there are no more small and medium enterprises, which are one of our proxies of economic development, although they are more productive. So we interpret this result as an effect on the intensive margin that probably has to do with knowledge spillovers, but this is speculative. I will have to say something about this later. As for the firm level analysis, our evidence that science cities still spur innovation, also in other firms that are located close to a science cities but not inside the science cities, our evidence is more limited, and we probably need to do more work on that. So I'll skip the literature. for the sake of time, let me talk about those science cities. For those who don't know about that, well, in the context of the Cold War, the Soviet government aimed at compete on strategic and military-focused R&D with the USA. What was the model of innovation that the Soviet government tried to establish? They created a set of enclaves of urban areas that were specifically devoted to R&D. Like you might be familiar with one company towns in Russia and in the USSR. I am probably less familiar with that, but those are like one company towns where the company there is some specific R&D type of project or as you can see, the main research areas for these science cities were mostly related to something that has to do with the military, like rocket science and space. Well, yesterday was the day of the cosmonauts here in Russia, so you probably understand what I'm talking about. We rely on historical research by a historian here at Moscow, Agiriechu, and I can't pronounce his name very well. But we've been able to find out what the general characteristics of these places were. Generally, they were set in places of Russia where they had a higher human capital and economic development than other localities, but sometimes those places were established in more remote areas for strategic and military considerations. Like as I write here, isolated and remote areas were preferred for basic science activities and cities that were devoted to highly secretive projects. At the extreme, those places were closed to outsiders and they were only reported on classified maps. So other political factors were at play in determining what was the location of these science cities. For example, a subset of those places were the Akademgorodki in Siberia, and they were set there for fostering the local development. So this informs our empirical strategy. Our idea is that at the margin, for two cities that were similar to each other in terms of ex ante observable characteristics, the location was chosen due to factors that have nothing to do with potential for economic development. And that is the reason why we apply a matching strategy to estimate the long-run effects of this policy. And this is a map that shows you the location of science cities. As you can see, most of them are clustered in Moscow or in the Urals area. But this geographical dimension is taken into account in our empirical strategy, as I will show you later. So, okay, this slide is not super informative. Probably it's more policy related. One thing I want to mention is that following the dissolution of the USSR, public support for R&D collapsed dramatically. We have data that show that funds dried up to 80%. We interpret this as a discontinuation of the policy. So if there is any long-run effect, this has something to do probably with more consequences in terms of local development or local human capital than direct funding by the direct continued funding by the Russian government. We have more robustness checks to assess this. So speaking of data, we assemble our list of science cities using a combination of sources, primarily this historian and geographer Agiriechu that I have mentioned. We combine the data set on Russian municipalities at the rayon level using different sources, and we also use the BEEPS data from the EBRD matched with Orbis of Bureau Van Dijk for our firm level analysis. Let me spend just 30 more seconds. I'm so much time constrained on the municipal level data. So as you can see, there's a lot of work behind it. We assemble geographical information, population information from the Soviet times using the first Soviet census after World War II, data on factories and R&D institutes and universities that are historical again in the time frame when those science cities were established between World War II and the early 60s. And then we also have data at the rayon level about current outcomes of Russian municipalities, including population, patents from the EPO, foreign registered patents that were realized in Russia, as well as our nighttime lights, which is one of our proxies for economic development of Russian rayons, given that we are unable to access accurate GDP data at the rayon level. And additionally, we also have data from the Russian SME census of 2010, from which we extract several proxies of economic development, like the number of SMEs, the densities of SMEs in the population, as well as the labor productivity of SMEs. So this is our empirical strategy. Again, we use Mahalanobis matching. Mahalanobis matching basically selects places that are close to each other in terms of all our observable characteristics that I have just mentioned, both geographical and historical. And the idea is, again, to compare apples with apples rather than apples with oranges. The results are very similar if we perform propensity score matching, which probably more people among this audience are familiar with, but we feel that this methodology is more appropriate to this geographical context, and we motivate this in the paper because it better allows to match on coordinates and the geographic dimension. The identifying assumption is motivated on the historical background. So our idea is that if we condition on these historical factors that have to do with possibly have to do with future economic development, the selection of a place for being a science city had to do more with political and military and strategic factors that are unrelated to future economic outcomes than anything else. And this is what motivates these conditional independence assumptions that is behind our matching strategy. So this shows you a map of our matched localities. Probably this can be improved a little bit by removing links that are too further away. But we feel that to a first degree of approximation, this is good. As you can see, places in Moscow or in the Moscow area are matched with localities that are somehow in the Moscow area as well or in neighboring oblasti. And some places are really matched to other places. I can name a few examples, but you probably can see this from the map. So here's our first set of results. Like as you can see, our matching strategy finds zero effects for several variables for which in the whole sample there are significant differences, but at the same time it also finds significant estimates despite the matching. In particular, you can see that for both our patent measures, science cities today are still more innovative than comparable locations. This probably may not be that surprising, but we also find that they host a more educated population, both in terms of the graduate share and the PhD share of the population. This is not to be taken for granted because people might have migrated after the collapse of the USSR. And in terms of our proxies for economic development, those places do not seem to host more SMEs. They do not seem to host more SMEs per population, but these SMEs seem to be more productive in terms of our labor productivity measure. And in addition, our night lights measure, which is a widely used proxy for economic development, is statistically significant. An exercise that we do is we remove from the analysis the current naukogrady still financed by the Russian government. I'm sorry. Recently, the Russian government has resumed a policy of direct support for some previous science cities, but just a minority of those that were in the past. If we remove them from the analysis, our coefficients from the patent outcomes decrease a little bit, which is to be expected, but all the other coefficients look almost exactly as before, with some exception for the night lights measure. But again, this means that probably the results that we find do not depend on the current governmental support, but we interpret them as long-run effects. We also have a firm level analysis. I will almost skip this because, as I said, it's not our main analysis. We make a descriptive analysis of the effect that being located closer to a science city has on innovation and firm performance outcomes of firms. We use a distance decay specification, which is really descriptive in nature. We do not try to correct for endogeneity. But we unfortunately cannot find that nice result as before. The best we can do is that there seems to be a relationship between firm innovation and the closeness a firm is located to a science city using our BEEPS data, but really no more than that. Also, no results with for other measures of firm performance. So I'll skip this because this firm level analysis is more work in progress, and probably it's not the best data to assess this effect. I'd rather talk to people who are more expert about this, but just let me get to the conclusion since I do not have that much time. So we find that science cities still host a more educated population today, but they are not significantly larger than historically similar localities. They are more innovative, and they also do better in terms of our proxies for economic development. We interpret this as an intensive margin effect rather than an extensive margin effect because we do not find those science cities to have more firms, but rather those firms are actually more innovative. So it's not an entrepreneurship effect, it's a productivity effect. And the results do not change that much when we remove current science cities from the analysis. And the firm level results are not that good, as I said. Now, most interesting and important slide. How do we interpret this result? I have a very specific urban economics model in mind. It's the Glaser-Gottlieb model from 2008, which has inspired lots of empirical research in urban economics afterwards. The idea of this model is that, okay, suppose the government finances employment and industry programs in certain localities, the government will be probably able to attract more workers there, but after the financing of this program dries up, those workers might move again elsewhere because the better employment opportunities will have terminated. So in light of this model, we interpret this result as follows. Since we still observe that in the past science cities, there is a more educated population, the results are consistent with the long-run shift of the spatial equilibrium. What is the story here? The place-based policies of the science cities have changed the local employment, and but thanks to knowledge spillovers that has created this is allowed by the Glaser-Gottlieb model here. Thanks to knowledge spillovers, the average firm in the local areas is more productive than elsewhere. So still, these places provide better opportunities for local workers, and that might have made it easier for people to stay rather than move elsewhere. And therefore, we do not observe the return to a pre-policy equilibrium. Now, however, that might also be due to other factors like frictions to the mobility of workers, but we have not the opportunity to assess this for the moment. So this is the current state of our research. We hope to improve it in the future, and thank you for your attention. Спасибо за внимание. And my Russian language skills are still limited, unfortunately. And if you'd like to have the current version of our paper, just email any of us, and I'm happy to take questions. Okay, thank you, Paolo.
Is there any question on this presentation? We have one.
Thank you. My question is, what was the initial purpose to engage into this firm level analysis actually in the study? Because your framework is already so sophisticated, and why do you need that? And a second comment there, as we experimented with the regional data, in fact, the only and the most significant regional-based variable is the, let's say, average wage or regional domestic product per capita. It kind of kills all other heterogeneity usually on the firm level of propensities and other effects of innovation. Just a comment.
So Yeah, the reason why we engaged in a firm level analysis in the first place is because we had no municipal level data before that, and we made a huge effort in the last year to assemble this data set. Before that, we only had beeps, and we struggled with it. As you say, I think both of us are familiar with this kind of data and trying to fit innovation models on this data, and it's really difficult. And it might be an issue with the data. I guess it's more an issue with the institutional context and the country we are analyzing. We hear that we try to improve with the help of policies, but this is so much the best we can get. And yes, it's really difficult. I agree with you, and I'm not that big of a fan of the CDM model applied to Russia after I have tried it, but I like that you are making progress on that. But the real focus of our paper for the moment is the municipal level analysis, not the firm level one.
Paolo, can I ask you, do you have numbers on the subsidies that went to these cities during the Soviet era?
We have tried to access it, and we asked Tatiana Mikhailova from RANEPA. She seems to be expert of this kind of things. She said that if you want these numbers, you need to do archival research here in Moscow, and it's really difficult because the information is really obscure. So we struggle with this. We would gladly take any help on that if any person would collaborate on that. But we have no data on those.
But many of them were secret, you know. I mean,
that's the issue.
So having some of them having more educated population and being more productive vis-a-vis others that you compare to, it's a sort of, as you see today, if you had that data, you could analyze on the margin if they are more productive, right? Because they may have taken so much more money than the rest that it doesn't really matter.
Yeah, it's a possibility, but what we have in mind is the large collapse, and we have some background story in the paper of public support to these places that happened after 1991. And according to this urban economics framework that I have cited at the end, if this support had terminated at some point, those workers would have gone elsewhere for some reason. If they have not, there must be for some reason. It might be that those places were still supported to an extent, or it might be that those guys maybe try to look for different opportunities for employment, and they use their human capital skills to create better firms.
Okay. All right, very good.
This is one of those areas where case study evidence could also help answer some of these questions. I mean, a lot of this, the focus is on the municipal governance, but there's also a lot of individual incentives for and ethics of work for the Russian scientists at the time, which may be different from today. So just to say that maybe this kind of research could be combined with case studies on the science cities in Russia. I know some researchers in the UK have worked on this. So,
yeah, I'd be happy to do that. I'm not an expert of case studies though, but we have anecdotal examples in the paper.
Okay, thank you very, very much.
Thank you.
So we move directly to Stanislav Zaichenko on human resources.
Hello, dear colleagues. Thank you very much for opportunity to discuss this topic today. Actually, it is based on the same information base as research presented on previous April conference. However, it is not devoted to a kind of review, but mostly focused on some particular problem. And the main research question, the main problem is the impact of science-based activity into technology transfer activity and correspondence with respective human resources. This topic actually is connected with various discussions. First of all, discussion on science-based activity itself, its role in innovation. Yesterday, Professor Kuzik discussed the problem of small impact, small fraction of science-based activity in innovation vis-a-vis very high value added from this mode. Another topic is the impact from academic human resources in terms of form of collaboration, form of knowledge codification, way of interaction, and so on and so on. It's really a big front of research at the international level as well as in Russia. And a more specific discussion is on staying alone research institutions, which in Russia is often called NII. Institutions which rely on own research base and operate separately from academic sphere, from universities, and from the real sector of economy. Kind of sectoral, applied, sciences-oriented research institutions, which form a very large portion in the Russian S&T system. But still, it's not a purely very Russian case. In many international studies, you will find such forms which more often are called as research and technology organizations, and sometimes they are discussed as a new form of centers of excellence, which are not just kind of ordinary intermediaries in technology transfer, but sources of customized, adapted knowledge. In some other studies, they act as a transitionary stage from public sector research institutions towards whatever, maybe failure stories as well. So it's also subject for a wide discussion. On the other hand, we have a policy framework in Russia which also sets up benchmarks for performance of R&D, also in academic sphere, in university science, as well as remuneration and encouragement for research activity of young researchers. So I'm talking about the presidential made decrees, first of all. Also, we should consider the framework for efficient contract in science, which also addresses issues of encouragement of scientific work of research personnel, and impact particular initiatives in encouragement of young researchers, of talented researchers and teams, including Statement 2020 and mega grants. And also on the strategic level, the issue of human resource in in STI is being more and more articulated. So this study is aimed at a quite modest objective, just to tie together the theoretical base with available empirical base in order to clarify somehow the evidence base for the current policies related with these issues. So the first task is to clarify the correspondence between science-based outputs and technology transfer activity in Russian applied science sector, and also to detailize the human resource dimension of this science-based activity, which can be useful for more precise targeting of related policies, and also in establishing more comprehensive impact evaluation tools, just to get understanding of what to estimate and how. So this discussion is based on longitude monitoring survey, which is a complementary part for the survey presented by my colleague Vitaly Rudь, but it observes not firms but research and technology organizations, more precisely research performing organizations, including higher education institutions and institutes of Russian Academy of Sciences. Actually, it's not designed for some particular studies on human resource or on technology transfer performance itself, but it's a very extensive database, including many aspects, including innovation performance, research performance, resource base of various kinds, networking activities, linkages, and so on. So the contribution from this insight is that we are able here to highlight not only graduates, university graduates, and faculty staff as categories of academic human resources, but also include PhD students. Here we name these categories candidate of science students, not only extramural to the reporting organization, but also including their own candidate of science students, and also to control the impact of the relationship with the academic human resource inflows. We can introduce alternative sources, including specialists from industrial enterprises, from the customer side, and also researchers from other competing research and technology organizations. University graduates still is the most popular source for new researchers for Russian RTOs, but intramural and extramural candidate of sciences students together also form a substantial inflow source, and what is important, these people already have practical background in research, and also are adjusted, more focused on profile, on agenda of the particular host RTO, research and technology organization. So also we can check various subsamples, not only general samples of research and technology organization, but also to test the correspondences on sample of transferring technology RTOs on RTOs which not necessarily transfer technologies on regular level basis, but still enjoy revenues from technology transfer activity, or also check the group of non-transferring research and technology institutions. Also, it is interesting to look from the point of view of ownership and size of customer enterprises. So let's assume that science-based outcomes do contribute, are really important for technology transfer activity, and just look in detail into predictors from the side of human resource inflows. Regardless, the main subsamples and the general sample, the probability to report scientific publications in the international indexed journals increases significantly and at high extent with hiring candidate of science students. So this is the most stable the impact, the most stable predictor, especially if we are talking about intramural own PhD students, which have a lower probability just to go out after the traineeship to go to some other institution. The same stable trend can be noticed for other subsamples, except subgroup of RTOs oriented towards serving SMEs, not SME, but small customer enterprises. And here it can be related with technical problems. It's a very small subsample from statistical point of view, and at the same time small customer enterprises themselves have quite particular profile from the point of view of absorptive capacities, and they require more often not science-based technological solutions, but just technology services outsourcing or something like that. Now let's also go back to the primary question. If we check for correlation of technology transfer activity with overall scientific publication activity as an output from science-based activity, it's still not high, even though it's significant. But if we move on to move towards high-level publications in the international index journals, the correlation coefficient rises twice, and what's more, it doesn't decrease or even increases if we add an additional condition of recruitment of intramural candidate of science students. If we add an opposite condition, still such kind of institutions exist in our sample, we just lose any correlation at all. Also, it's interesting to check if there is any correspondence with acceptance of policies and estimated expected effects from policies. From about 20 policy initiatives mentioned in our questionnaire, only 4 policies has perform some kind of significant correlations with the components of activity discussed above, and anyway the coefficients are quite low. Also there is so only 2 policies has some response from all 3 categories of criteria. So technology transfer, publications, and recruitment of PhD students positively. So this subgroups positively. More positively react to efficient contracts, contract network, framework, and also to encouragement of research activities under mega grant initiative. Activities of Russian Science Foundation is more appreciated by academically oriented RTOs, while support to technoparks and innovation infrastructure is more mentioned by technology transfer oriented ones. Anyway, of course, we cannot interpret this actually mainly preliminary outcomes in the way that RTOs which hire own PhD students forced them to publish in high-level journals and to provide research outcomes applicable for successful innovation and so on. Of course not. But still we can state that there is a visible group, a visible type of research and technology institutions which perform complementary nature of science-based of combining science-based activity with technology transfer, and this complementarity is being reinforced by engagement of new researchers from own PhD students. At the same time, we can state quite weak correlation, weak reaction of such kind of RTOs to public policies which are expected to assist somehow with this kind of activities. It can be related both with quite neutral estimations, actually estimations of effects in our sample by our RTOs is really quite neutral, and it makes it difficult to find out trends. But also it can be related with unclear effects themselves from these policies. So here we have some grounds to discuss the evidence for policy mix, for combining different kind of policies related with different aspects of these activities, or on addressing complex addressing of related policies, as well as or targeting initiatives related with clearance of PhD councils, assistance to joint research and technology centers, and so on. Okay, thank you.
Okay, thank you. We have very little time left for discussion here, but if there is any burning question, yeah. Yeah, if there is any burning question, we can ask one right now or wait for the end. Okay, you have?
Just could you clarify the for the technology transfer? I mean, from my knowledge, students get involved in different ways through spin-offs and through licensing and projects. The way you classified that, I could not really distinguish that. So could you explain?
Actually, it's a subject for the further investigation because here we used a specification of technology transfer, the very first position, strategic technology transfer. That means that research organizations just reported that they perform transfer of codified technologies for application in the real sector of economy for 3 years, so for some period of time on the regular level, not occasionally. But the questionnaire also allows to specify if we are talking about licensing, if we are talking about just providing technical outcomes or some other forms or channels for technology transfer. But actually it doesn't include a spin-off activity unless this opportunity exists for Russian research institutions, but there are other questions on networking activities and presence in existing S&T networks, which can be somehow applied also to identify such kind of transfer.
Okay, thank you. Thanks a lot. So let's have the last paper. Do we have the Vitaly Dementьев? Thank you.
Добрый день, уважаемые коллеги. Я понимаю, что у меня доклад, наверное, последний, да, я постараюсь очень компактно и дозированно то, что будет интересно, рассказать. И причем я посчитал, что рассказывать про реализацию государственных программ, послание президента на английском языке будет непатриотично. Тема моего доклада посвящена повышению эффективности расходования бюджетных средств на исследования и разработки как фактор, влияющий на реализацию научно-технической политики. Не буду подробно останавливаться на структуре, мы сейчас в разрезе при рассмотрении коснемся этих вопросов. Очень кратко остановился бы на схеме анализа. Схема анализа построена в логике международных практик и нашего законодательства, которое формирует структуру системы стратегического планирования. То есть, когда на самом верхнем уровне социально-экономические цели, определенные президентом в указах и в своих посланиях. Дальше стратегия научно-технологического развития. Инструментами реализации стратегии являются программы, государственные программы и федеральные целевые программы, которые входят в составе госпрограмм. И государственные программы оцениваются на разных горизонтах по-разному. То есть на краткосрочном горизонте мы оцениваем показатели, связанные с финансированием в первую очередь, ну, с ресурсами, с использованием ресурсов. На горизонте около 1 года у нас есть возможность оценивать показатели результативности неокров. И от года и до 6 и далее мы можем оценивать эффекты. Вот в среднесрочной перспективе это эффекты отраслевые, а в долгосрочной это социально-экономические эффекты. Соответственно, результаты, которые мы получаем при анализе эффективности, могут быть использованы для корректировки государственных программ и уточнения научно-технической политики. В соответствии с международной практикой мы выделили блоки показателей ресурсной обеспеченности, результативности, R&D, секторальных эффектов, ну, отраслевых эффектов и социально-экономических эффектов. При проведении анализа мы использовали зарубежный опыт. Опыт оценки эффективности, который применяется в США, когда проводится анализ достижения целей, анализ результатов, анализ расходования средств и эффектов. И европейский опыт, в частности программы «Горизонт 2020», да, оценка как раз осуществляется в рамках блоков показателей. К сожалению, российская практика не содержит методики, необходимые для проведения анализов расходования средств на R&D. Министерство экономического развития и Министерство образования, они используют методику, по которой они оценивают в целом эффективность реализации программы. Счетная палата Российской Федерации руководствуется стандартом, который тоже не содержит критериев оценки эффективности R&D. Наши исследования в какой-то мере восполняют этот пробел. Все вышеперечисленные практики зарубежные, в том числе группировка показателей по блокам, необходима была для формирования методики. Ну, во-первых, мы соотнесли виды научной деятельности с уровнями готовности технологий и пришли к такому выводу, что на начальных стадиях жизненного цикла технологии самой технологии нет. Сначала проводится исследование. Это вот с 0 до 3 стадии. С 4 по 7 появляется образец, который проходит дальнейшие исследования, испытания. И на 7 стадии появляется предпроизводственный образец, который потом идет в производство. Данные знания нам были необходимы для того, чтобы сформировать такую вот матрицу, в рамках которой мы распределяли показатели по группам. То есть у нас по вертикали 3 блока. Блок ресурсной обеспеченности, блок результативности отрасли или программы. И третий блок – это социально-экономические эффекты. И мы видим, что для первой группы показателей, это показатели, связанные с исследованиями, фундаментальными исследованиями, характерны только показатели ресурсной обеспеченности и публикационной активности. Для второй группы также ресурсная обеспеченность и концентрация показателей, которые характеризуют результативность, она выше. То есть здесь патентная активность, риды, результаты интеллектуальной деятельности. И третья группа показателей уровня готовности технологий, она самая насыщенная. Я на этой группе подробно не буду останавливаться, потому что она выходит за рамки НИОКРов, ну и РНД. Обращу ваше внимание на нижний горизонтальный сектор, который характеризует участие государства в этих блоках уровня готовности технологий. То есть в первой группе государство полностью за счет бюджета финансирует все исследования. В второй группе 50% участия. И в третьей группе минимальное участие 10%. Здесь важно посмотреть с позиции реализации стратегии на применение этой методики. В конце 2016 года была указом президента принята стратегия научно-технологического развития, в которой выделяются 3 группы в рамках 2 этапов, 3 группы целей. Первая цель – это значит, проведение фундаментальных исследований и формирование задела в виде новых технологий. Вторая цель в рамках уже следующего этапа – это повышение экспортного потенциала. И третья цель – это создание новых отраслей и секторов экономики. И мы видим, что государственные программы, которые реализуются в Российской Федерации, они по-разному работают на разные цели. То есть на первую цель в основном работают 3 программы. Это программа научно-технологического развития, программа развития здравоохранения и программа развития образования. На экспортный потенциал и на создание новых отраслей секторов экономики работают все отраслевые программы. В рамках исследования нам пришлось формировать большую базу данных, что называется, по крупицам собирать информацию. Это всевозможные источники, содержащие информацию о государственных программах, о федеральных целевых программах, данные о бюджетном финансировании, данные министерств, содержащих показатели результативности и так далее. после того, как мы сформировали базы данных, нам удалось выделить приоритеты финансирования из бюджета исследований и разработок. Ну, во-первых, в 2015 году общий объем финансирования в государственных программах был 366 миллиардов рублей. К 2019 году этот объем финансирования сокращается. В то же время мы видим, что структура расходов меняется. Если в 2015 году вот представленные 11 программ в совокупности составляли 95% расходов федерального бюджета, то к 2019 году их доля еще больше увеличивается. И причем меняется акцент. Акцент финансирования. Государство больше средств выделяет на программу развития науки и технологий, на образование и здравоохранение и в меньшей степени финансирует отраслевые программы. Ну, там за исключением электроники, где есть рост. Также, благодаря базе данных, мы определили наукоемкость программ. То есть выделенные 11 программ являются очень наукоемкими. То есть доля финансирования неокров в их структуре очень высока и колеблется от 5 до 90%. Также мы проанализировали инструменты, которые применяются для первой и второй укрупненной группы уровня готовности технологий. Ну, то есть в первую группу исследования у нас попадают фундаментальные исследования, в группу разработки, это вот с 4 по 7 TRL, попадают прикладные исследования и разработки. И мы видим, что фундаментальные исследования в основном финансируются через субсидии бюджетным организациям. Также есть небольшое финансирование научной инфраструктуры. А вот вторая группа исследований и разработок, она финансируется в основном за счет прямых закупок неокров и субсидий коммерческим организациям. Также мы посмотрели, как меняются приоритеты. К 2019 году мы видим, что расходы на национальную экономику сокращаются, и государство больше средств перераспределяет в пользу фундаментальных исследований. Здравоохранение, расходы на здравоохранение сохраняются на прежнем уровне, на образование небольшое сокращение идет, и общегосударственные расходы на неокры, они тоже сохраняются примерно на прежнем уровне. Дальше мы разработали такой вот механизм, который позволяет определять, в каких программах, на какие цели, через какие механизмы требуется софинансирование. Потому что мы видим, что по предыдущим слайдам бюджетное финансирование сокращается, и необходимо формирование механизма, компенсирующего падение бюджетных расходов. И значит, в первую группу перераспределяется бюджетное финансирование, а вторая группа компенсируется за счет привлечения внебюджетного финансирования. Далее мы провели анализ показателей всего в 11 программах их порядка 700. Мы выделили 96 показателей, которые непосредственно характеризуют R&D. Сформировали критерии, по которым мы не можем все показатели включить в анализ. Но, например, мы исключили показатели, по которым банально отсутствуют данные, волатильные показатели, показатели, по которым имеется там, в 9 раз отклонение плана от факта. Вот. Мы данные показатели отбросили, и в результате у нас получилась выборка из 68 показателей. Мы провели частотный анализ в разрезе групп этих показателей по программам. Мы увидели, что высокая концентрация показателей, которые характеризуют результаты интеллектуальной деятельности, они практически во всех программах встречаются. Также показатели патентной активности часто встречаются. Публикационная активность меньше, но и там всего лишь 3 программы, которые работают на фундаментальные исследования. И в основном показатели ресурсной обеспеченности. Данный набор показателей данные показатели мы использовали для определения интегральной эффективности. Мы ввели 4 критерия, по которым мы оценивали эффективность. Это средняя скорость достижения плановых показателей в отчетном году по сравнению с конечными показателями, которые содержатся в программах. То есть, если в отчетном году показатель, индекс достижения показателей выше средней, то это хорошо. Потом показатели софинансирования, показатели достижения ключевых событий применили и показатели достижения плановых значений мы использовали как 4-й критерий. Данные критерии мы свели в таблицу, и мы видим картинку по результативности программ. Причем хочу заметить, что это результативность, которая касается показателей НИОКР. Мы ради эксперимента сравнили результативность показателей по 700 показателям. Там картинка, конечно, другая. То есть за счет отраслевых показателей некоторые программы выглядят чуть лучше. Но по показателям НИОКР картинка следующая, что у нас самая эффективная – это программа развития электронной промышленности, развития науки и технологий, авиационная программа, в части НИОКРов, судостроение, средняя эффективность у фармацевтической программы, образования и развития промышленности. И программы, такие аутсайдеры, это экономическое развитие здравоохранения и развитие атомного энергопромышленного комплекса. По результатам исследований мы сформировали рекомендации. Мы рекомендуем министерствам, которые отвечают за реализацию программ, смотреть на критерии, которые характеризуют интегральную эффективность. Потом в рамках частотного анализа мы предложили дополнить программы показателями, где они отсутствуют, там в группах показателей. Ну и дали предложение по корректировке методики. Спасибо.
Unfortunately, I'm afraid that we are already beyond the time. So I would urge you to actually talk individually to the presenters if you have questions for them for the presentations. So thank you very much for coming, and we will see you a little bit later. Thank you.